Okay, so now let's do some exercises. So first one, f a b to r absolutely continuous. A, show that TAB of f equals integral AB mod f dash dm1. So we proved this for continuously differentiable functions, so it's also true for absolutely continuous functions. B, PAB of f equals integral AB mod f f dash plus dm1, and NAB of f equals integral AB f dash minus dm. So solution: A, f absolutely continuous implies f is BV. This implies integral AB mod f dash dm1 is less than or equal to TAB of f. So proved in lectures. We've already seen this. Okay. Now f is absolutely continuous. So P equals A equals x naught less than x1 less than xn equal to B, any partition. Then you have f of xi minus f of xi minus 1 equals integral over xi minus 1 f dash dm1. That is just by absolute continuity. And therefore you have TPF, which you have to take the modulus which is equal to sigma I equals 1 to n mod f xi minus f xi minus 1 less than or equal to sigma I equals 1 to n integral xi minus 1 mod f dash dm1, which is equal to integral AB mod f dash dm1. And therefore this implies that TAB of f, which the supremum, is also less than mod f dash dm1 over AB. So that completes the proof. You have both inequalities. You have one here, you have one here, and therefore that does the trick. Okay, B. So you have that FB minus FA equals PAB of f minus NAB of f. But that's equal to integral mod f dash dm1 over AB equals integral not mod f dash, equals f dash dm1, and therefore that's equal to integral AB f dash plus dm1 minus integral over AB f dash minus dm1. And you also have TAB of f equals PAB of f plus NAB of f, and that's equal to integral mod f dash dm1 by A, and that's equal to integral f dash plus over AB dm1 plus integral over AB f dash minus dm1. And consequently you have PAB f minus NAB f equals integral over AB f dash plus dm1 minus integral f dash minus dm1 over AB, and PAB of f plus NAB of f equals integral AB f dash plus dm1 plus integral ab f dash minus dm1, and that completes the proof because you simply solve for PAB and NAB from these two. Second question, f AB to R bounded variation. For x in AB, define Vf of x equal to Tax of f. A, f continuous implies Vf continuous. B, f absolutely continuous implies Vf absolutely continuous. So solution, we will prove the continuity by showing the left and the right continuity. So let A less than or equal to x less than b, epsilon greater than 0, then there exists a delta positive such that t minus x less than delta implies mod ft minus fx less than epsilon. This is the usual continuity. So now let t belong to x, t be bigger than x and t minus x less than delta. Okay, so given any partition, refine it to include partition of AT, refine it to include x as the penultimate node. Okay, so what do you want to do? You have A equals x naught less than x1 less than etc less than xn minus 1 which will be equal to x less than xn which will be equal to t. Then sigma I equals 1 to n mod f of xi minus f of xi minus 1 is less than or equal to sigma I equals 1 to n minus 1 mod f of xi minus f of xi minus 1 plus mod fx minus ft, and that is less than or equal to, this will be Vf of x because the last node is for here is up to n minus 1, that is equal to x, so that is less than or equal to Vfx plus fx minus ft is less than epsilon, and this can be done for any partition, and therefore you have, this implies that Vf of t is less than or equal to Vf of x plus epsilon. But on the other hand, you know that Vf, the total variation, is of course a monotonic function. The more longer the interval, more partitions are there for the supremum, and therefore Vf of x is anyway less than this, and this is true for all t minus x less than delta, and this implies continuity from right. Now for the continuity from left, so you take any partition P equals A equals x naught less than x1 less than etc less than xn equal to x, partition of Ax. And now such that, so let be a partition of Ax such that sigma I equals 1 to n mod f of xi minus f of xi minus 1 is bigger than Vf of x minus epsilon, because the partition is the supremum is Vf of x, so I can always find a partition which is bigger than Vf of x minus epsilon. Now let xn minus 1 less than t less than xn equal to x, and x minus t less than delta. So sigma I equals 1 to n mod f of xi minus f of xi minus 1 is less than equal to sigma I equals 1 to n minus 1 mod f of xi minus f of xi minus 1 plus mod f of t minus f of xn minus 1 plus mod f of n minus ft, and this is equal to f of x, remember. Okay, I am just used the triangle inequality. So this is less than or equal to Vf of xt, Vf of t, because I have a partition here and then I have added t as a point, Vf of t, and the last term is less than epsilon. Okay, and the left hand side is bigger than Vf of x minus epsilon. So Vf of x minus 2 epsilon is less than or equal to Vf of t, and that is less than or equal to Vf of x because x is bigger than t. Okay, so x is bigger than t, and therefore once again this is for all x minus t less than delta, and this implies continuity from left. So this implies that Vf is continuous. B, f is absolutely continuous on AB, and that implies f is absolutely continuous on AX for any x less than or equal to b, a less than or equal to x less than. Okay, so you have that Vf of x is t a x of f, which is equal to integral ax mod f dash dm1. Now mod f dash is of course integrable, and so Vf of x is nothing but the indefinite integral of an integrable function, and therefore this implies that Vf is AC. Three, a monotonic function is said to be singular if f dash, so a monotonic function f dash equal to 0 almost everywhere. So example is the Cantor function, which is a monotonic increasing function, which is the derivative 0 almost everywhere. If f is monotonic increasing, show that it can be written. So let me, so as not to give you confusion between the two f's here. So this is for the if f is monotonic, show that it can be written as the sum of a monotonic increasing function, sorry, a singular function and an absolutely continuous function. Solution. So f monotonic increasing implies f dash exists almost everywhere, f dash greater or equal to 0, and integral f dash dm1 over ab is less than or equal to fb minus fa, implies f dash integrable. define g of x equals integral a to x f dash dm1, and this implies that g is absolutely continuous. And also you know that g dash equal to f dash almost everywhere. Now you set h equals f minus g, then h dash equal to 0 almost everywhere, and you have, if x is less than or equal to y, hy minus hx is the same as fy minus fx, h is fx minus integral x to y f dash dm1. But that is greater or equal to 0 since f is monotonic increasing. The integral of a monotonic increasing function is less of the derivative is less than or equal to the values of the endpoints. So this is this thing. So this implies that h is singular because it's monotonic increasing, it's monotonic and has 0 derivative. G is absolutely continuous, and f equals h plus g. For f from 0 1 to r continuous, and f absolutely continuous on epsilon 1 for every epsilon positive. A, show that f need not be absolutely continuous on 0 1. B, in addition, if f is BV, show that f is absolutely continuous on 0. Solution. So the first one we will give a counter example. So let us take f of x equals x square sine 1 by x square, 0 less than x less than or equal to 1, and 0 for x equal to 0. Then we know f is not BV, we have already seen, and this implies f is not absolutely continuous on 0 1. But for every epsilon positive, f is C1 on epsilon 1 implies f is absolutely continuous. Okay, so this is A. B. So now we have to show, now we are given that f is BV implies f dash is integrable. In fact, you know that integral mod f dash dm1 over AB, we saw this in the beginning also, is less than or equal to TAB of f, which is less than plus infinity. So now let x belong to AB and let 0 less than epsilon less than x. So f of x is equal to f of epsilon plus integral epsilon to 1 f dash dm1, which is equal to f of epsilon plus integral 0 1 chi f dash chi of epsilon 1 dm1. Now as epsilon f of epsilon goes to f of 0, this is continuity. As epsilon goes to 0. F chi epsilon 1 converges to f as epsilon goes to 0. And mod f dash chi epsilon 1 is less than or equal to mod f dash, and this is integrable. Therefore, by dominated convergence theorem, as epsilon goes to 0, we have fx equals f0 plus integral 0 1 f dash dm1 implies f is absolutely continuous on 0 1. So with this we will conclude this chapter. Next time we will start a new topic.